Hello and welcome to today's webinar, Nightmare on GIS Street, GNSS Accuracy, Datums, and Geospatial Data, brought to you by GPS World, Geospatial Solutions, and Platinum sponsor Hemisphere. I'm Bethany Chambers from North Coast Media, publisher of GPS World Magazine, and I will be your event manager. Before we get started, I want to let you know that today's webinar will be recorded. You are currently in a listen-only mode. The recording will be available 2 weeks from today on both of our websites, gpsworld.com/webinars and geospatial-solutions.com/webinars. A link to the on-demand recording will also be emailed to you when it is available. At this time, I'd like to acquaint you with the ways in which you can participate during today's presentation. Please notice in the lower left-hand corner of your console that there is a Submit button. We encourage you to ask questions throughout the presentation. Just type in the text box at the bottom left, then click Submit to place your question in queue. Many of you submitted questions during registration, and it's great to have so much participation already. Many of your questions will be covered in this webinar. We may also answer some of them in an upcoming issue of GPS World Magazine or in one of our many e-newsletters. We strive to answer as many of your questions as possible. Finally, if you experience any technical difficulties during today's event, select Help to submit your issue, and Assistant Producer Rick Aldrich or I will personally assist you. Now I'd like to turn today's event over to our moderator, Survey Scene Newsletter Editor Eric Gakstatter.
Hey, thanks, Bethany, and thanks for everyone for attending today's webinar. This is a super exciting one for me, and one that a subject that I've written a lot about over the last few months, and in fact, one of the panel members, Kevin Kelly, and I had a sit down at last year's ESRI user conference last summer in San Diego, and sort of talked out this issue, and I promised him that I would try to gain some traction on this and bring this issue up to the user community, and I think it's super important. But I'm happy to have some really distinguished panel members here with me today. Michael Dennis, Geodesist with the National Geodetic Survey. Again, Kevin Kelly, Geodesist with ESRI. And then Craig Greenwald, Technical Director at GeoMobile Innovations. I worked with Craig a number of years back, and he was also on the ESRI ArcPad team for a number of years. And so all these folks have really a lot of knowledge about this subject, far surpassing what I know, and I think that's the value of me, is I can bring people in, hopefully, that know a lot more about this than I do, and really bring to light this issue. So here's I just displayed the agenda for today. I'm sort of going to try to frame this whole subject a little bit just for the next few minutes, and then I'll pass it on to Michael, who will discuss sort of the challenges of horizontal datums given the background. And then on to Kevin from an ESRI perspective of integrating high accuracy data into the ESRI workflow. And then Craig from a user perspective as a consultant and a developer of issues or subjects that he's run into along the lines of datum and high accuracy data and that sort of thing. And then we really received a tremendous amount of audience questions upon registration. And we're going to try to hit some of those because some of them are really neat and are worthy of discussion. And also, if you have any questions, you can use the webinar tool to ask those, and we'll try to hit as many of those as we can. So just to frame this issue a little bit, from my perspective, when I ask myself, hey, why should folks even care about this issue? Well, number one, and I've written about this for a few years now, is the cost of acquiring high-precision geospatial data is really declining. And you see that with the declining cost of high-precision GNSS receivers, the declining cost of 3D scanning terrestrial LiDAR as well as airborne LiDAR. And also UAVs are coming on strong. They'll bring in some high-precision data also. And so, what's happening is when folks are collecting this data and sort of overlaying them on their legacy base station or the base data, geospatial data, you're starting to see some disparity. Things don't quite match up. And I gave some anecdotal examples in some of the articles that I've written, but over the last 25 years, I've run into this case a lot of times where where the GPS data or other types of data are brought into the base map, and they don't match up. And that's probably the number one question I get from folks even today is, hey, why doesn't my data line up? And this is an ongoing issue, and it's not just the datum, horizontal datum issue itself, but it's the technology is becoming that much better and that much more accurate that it's rendering legacy data sort of obsolete. And so I guess the question at the end is, how do you make good quality decisions when the data is so disparate? When you can't match data up. And I'll give you a good example. Is currently I'm working with a water utility company, and they're starting to use, they have this certain base map based on all kinds of different data sources. There's ortho imagery from the state. There's census data for street center lines, and then there's their own water main infrastructure that they have. And so they're starting to integrate RTK, which is plus or minus a couple of centimeters, RTK GNSS in real time, and they're taking their mobile map out in the field, and they're finding that it's not lining up with some of their base data, and part of that is this datum issue that we're going to discuss. But other parts of it is just because the legacy data is just so inaccurate compared to what they can collect today. So, boy, they ask themselves, how do we make good quality decisions? How do we interpret this data so we can make good quality decisions? And it's certainly a challenge. Now, this next slide, and I use this phrase a lot, is a picture is worth 1,000 words, but kind of not in some cases, because people tend to believe aerial photography or ortho photos as being the default, and Google Earth is a great example. They think because they can see it that it's the most accurate data, and so if you bring in some accurate GNSS data or other types of data and it doesn't agree with the ortho photos, then they think that by default the data they brought in is inaccurate. Well, in a lot of cases, and maybe one of the other panel members can comment on this, is that the ortho photos really aren't always that accurate. Especially when you start looking at Google Earth. But even pretty high res ortho photos can be off 2 or 3 or 4 or 5 feet. So that's an issue. Is what piece of data do we believe within our GIS? And to really make that determination, you have to understand the source of the data. How was it collected? Which datum epoch was it referenced to? That sort of thing. And then how do you determine which one is the truth? And what I always fall back on is occupying survey marks on the ground to understand how those relate to your geospatial data, because those really are the truth. But it's not all survey marks. And this is interesting because I've run into folks who said, well, hey, I went out and occupied a survey mark, but it really doesn't, I really can't make sense of it. And the bottom line is that all survey marks aren't created equal, and Michael can probably comment on this here in a bit. But just because you found a survey mark on the ground doesn't mean it's got current coordinates occupied by GPS. They could be scaled off of a paper map. So there's all different types of quality of survey marks, and so just because there's a disk on the ground doesn't mean you should use it, or you should think it's more accurate than what you have. In this last slide here in this introduction for me, before I ask a poll and pass it off to Michael, is I'm displaying right now a data sheet from the U.S. National Geodetic Survey that describes a particular survey control point, and this is one that I actually occupied out in Colorado, I believe. Yes, when I was in Colorado a couple of months ago. I was looking for a survey mark that I could occupy with a GNSS receiver and test out a real-time data stream. And so, of course, I wanted to find a reasonably close survey mark, but more importantly, I had to find the right survey mark. And the magic text to me in this sheet is down there at the bottom, where it says the horizontal coordinates were established by GPS observations and adjusted by the National Geodetic Survey in June 2012. So what that tells me is a couple different things. A, it tells me that the survey mark is in such a location that it's compatible with GPS or GNSS occupation. It's not located under a tree or right next to a building or that sort of thing. There's a reasonably clear view of the sky. And number two, it tells me that the coordinates that are in the data sheet are reasonably current, occupied by GPS, and were adjusted. And so it's a very good benchmark for me to compare my own GPS observations to these particular coordinates. So this leads me into the first poll question that I'd like to ask the audience. And the question is, how much of a problem is matching data with disparate datums in your organization? Just to get an idea, how often do you run into this issue? Is it a big problem within your organization? Is it a mediocre problem? Is it not a problem? Or the last one is maybe you don't know it's a problem. So go ahead and select one of those, and then I'll display the results to the audience. But anybody on the panel want to comment at least on this first area that I covered? All righty. I'm going to go ahead and push out the poll results. Okay, so I really didn't know what to expect there, so I can't comment on it too much. But most of you think it's somewhat of a problem. Personally, if someone asked me, I think it depends on the organization. But at least the ones that I've run into, the enterprise type organizations, it ends up being a big problem. And much bigger ones than I think people realize at this point, because there's such a huge amount of geospatial data out there, and it really varies in quality, in positional quality. So at this moment, I'd like to go ahead and pass the mic to Michael Dennis of the National Geodetic Survey, and he's got a few slides here he'd like to talk to you about. Michael?
All right, thank you, Eric. Hello, everybody. I'm taking on a pretty big topic here with a really small amount of time, and I'm going to try to stay within my assigned time constraints and see what we can cover. What I'm going to talk about are really datums, which is essentially how we connect data to the Earth. And actually on this, in this initial title slide, you see I have an image of the Earth there, and what you see are some contours showing horizontal differences between NAD 83, actually, its various incarnations, and our new geometric datum that we're supposed to have out in 2022. What it is essentially is a map of the difference between NAD 83 and quote-unquote WGS 84 right now, essentially, to give you an idea. And you can see it's kind of strange, and you can also see that it's associated with specific tectonic plates on the world, especially the North American plate here and the Pacific plate, and that the contours are very, very different. So we're into sort of a brave new world of positioning. And it's kind of I think this is a Chinese proverb. When the gods want to punish us, they make our wishes come true. Well, we've been wishing for more and more accurate data. Well, we got it, and now there's some other issues that we have to deal with. Go ahead, Eric.
All right, next slide is up.
All right, and I saw there was a comment in the questions and answers about the slides not coming up, so hopefully I'll leave all these up long enough that everyone has a chance to read them. First question, which I'm not going to answer in great detail, is what is a datum? And I think when this was announced, Eric said we're going to talk about horizontal datums. Well, we really don't use those types of systems anymore. We call them geometric datums because there is a height component, that is an ellipsoid height component. These are also called geographic coordinate systems, for example, in ESRI software and other software as well, other places. Really, it's just the basis for determining positions on the Earth itself. And the modern ones are four-dimensional. That is, they have latitude, longitude, and a height component, ellipsoidal height component, or you can transform that to so-called Earth-centered, Earth-fixed Cartesian coordinate system, XYZ system. They're interchangeable. And the fourth dimension nowadays is time. We can no longer ignore the time part of it, and I'll show you a lot more about that. One point of confusion is people conflate ellipsoids and datums. They talk about NAD 83, for example, uses the GRS 80 ellipsoid. But that GRS80 ellipsoid is essentially identical to the WGS84 ellipsoid, but those are not the same datums. They differ by about 2 meters. So that is a constant and persistent source of confusion, not just for that reason, but for some other reasons as well. And I'm going to deal with that directly. In fact, I'm going to use NAD83 and WGS84 as sort of the poster child for the complexity of relating datums to one another. One thing you can do with these datums is you can divide them into so-called, let's say, call them local and global datums. Local or regional datums for a specific part of the Earth, like the North American datum of 1983. That's ostensibly for North America, though it's also been extended to include the Pacific Ocean as well. But again, it's just for a part of the Earth. And that's a historical thing as well. Because in the past, before satellites, everything had to be, could be no larger than continental in size. And then there are global datums, which we've gotten since the advent of satellite technology especially, though there were some prior to that. And WGS84 is the classic example of a global datum, and a lot more on that as we go. Now, there's also vertical, or we could call them geopotential datums, but that's a complicated topic for another time that we won't cover here. Go ahead, Eric.
All right, we're up.
All right. Codependence. We have geospatial codependence. And the first step with that, of course, is admitting that you have a problem. A lot of people admitted that in this poll, which I was glad to see. Honesty is a good thing. Okay, datums. You know, a datum is an idea, and that idea has to be realized. And the only way to realize it is to connect it to the Earth through observations, whether those be terrestrial observations or nowadays GNSS observations. You have to make the observations. Those give coordinates to physical things on the ground, whether that thing's a brass cap or the face center of an antenna, a GNSS antenna. So we have these things, these datums, which are ideas. Let's say that WGS84 is an idea for a datum that was first realized in 1987. Well, since then, there have been 4 additional realizations of WGS84 as new data were used to get better and better coordinates. Same thing has happened with NAD83. They have been re-realized even though it's the same datum. This, again, is another source of great confusion, which I'll talk about some more. Now, we have all these datums all over the world. There's hundreds of them. We have data referenced to all these different datums, and people like to have their data line up when they put it all together, for example, in a GIS. Well, the interrelationships between those datums are datum transformations, which are just mathematical models for converting between the datums. And you need them when you combine data from different datums. But there are many, many different kinds, and they vary tremendously, from simple geometric shifts to ones that model complex tectonic motion and even earthquakes. So there's all kinds of stuff out there. The modern datum definitions can be extremely complex, and I'm going to focus on 2 in particular in this presentation. Next slide, please.
All right, there's some animations in here, so it may take a few seconds for it to load for folks.
Yeah, and it's all automatic, so you don't have to click through anything. Yeah, and it'll come up while I'm chatting here. First, let me give you a real quick history of the first one in there, NAD83. The original realization was completed in 1986 and almost entirely classic or optical observations. Later, in the 1990s, when GPS came along, it was readjusted to align it with the more precise positions that are possible with GPS. But we didn't do that in a nationwide way. We did it essentially state by state. And in those adjustments, we included the classical stations. Now, when 2007 came along, we did a national adjustment for yet a new realization of NAD83. Oh, I'm sorry, I didn't give a name to the first realization. There's multiple, but they're called HARNs, or high accuracy reference networks. Again, state by state, essentially. Then in 2007, we did the entire nation. This time it was GPS only. That's why the photograph of the surveyors on the Bilby Tower disappeared, sort of an end of a heroic era of surveying. And so we did that in 2007, got a new set of coordinates, a new realization, which has the confusing datum tag or realization of NSRS 2007 or CORS 96. That is very confusing, but they're essentially functionally the same thing. Then we did yet another one just recently, completed it in June of That's confusing too. We did one based on the cores and then adjusted the passive control along with it, and it's called NAD83 2011 for North America, or PA11 for the Pacific, and MA11 for the far western Pacific, for the Mariana Tectonic Plate. Again, only GPS. And it's the same realization this time for everything. The cores are not different than the passive marks. It's all one realization for each type, depending on the location. But it is not a new datum. It's still NAD83. It's just a new realization. Go ahead, Eric. And I see I need to get moving along here. I just wanted to show you the spatial extents of the U.S. National Spatial Reference System. You can see this is the distribution of all the control and the national adjustment of 2011. You see it's covering, obviously, continental U.S., Alaska, a fairly big chunk of the Pacific, all the way to the far western Pacific, and even some ties into South America. So it's a very extensive system. And the part in CONUS in Alaska is all referenced to the North America plate, actually the Caribbean as well. The Pacific, mid-Pacific's reference to the Pacific plate, and the Western Pacific's reference to Mariana Tectonic Plate. Next slide, please.
And just a note there about time, we're not limited to 65 minutes today, so if we end up going over, folks, and you want to hang with us, and we'll do so. So it's important to cover this issue, and it's a lot of stuff, so don't worry about time, Michael.
Okay, I'll try not to worry about it, but I can really get carried away, as anybody that's dealt with me in the past knows. And one thing, too, let me pause for a moment. Since, as you said that, I'm gone into some detail in that slide about NAD83 to give you a little bit of its history. And we could do this with datum after datum after datum, and we're doing it for two, NAD83 and WGS84. And this may be a lot more detail than people really even want to see. So part of my purpose here isn't that you'll walk away from this saying, wow, I really understand this stuff now, because you won't necessarily, but what I'm trying to give is an appreciation for how complex it really has become. And then the hard question really is, does it matter to you? And the answer, Eric already indicated it before, is it depends. Depends on what you're doing. So anyway, now that was NAD83 before. Now we're going to talk about WGS84, because I want you to know that it's not just the National Geodetic Survey that's doing crazy things with these datums. The U.S. Department of Defense is as well. So we're not alone in this. We're always trying to refine these systems. Again, history here. Original realization completed in 1987, and the intent at that time was to align it with the original realization of NAD83, and it was. They were the same. And everybody says that. They're the same. What people forget are the things in parentheses. They're the same to within, plus or minus.
I hate to cut you off there, Michael. It's Bethany cutting in here. We are having a brief delay in the slides here. So if we could, if you want to wrap up what you're talking about on this slide, and then Eric, do you want to moderate a few questions while we tech support these slides?
Sure. We're at the WGS84 slide right now. We're okay on this one?
Yeah, that's great. Go ahead and finish up that slide, and then take some questions while we get them back moving again, okay?
Okay. All right. So WGS84 is considered the same as NAD83, and everybody focuses on that nowadays, and it's true. But they forget about, or perhaps don't even know, that that's only to within plus or minus 1 to 2 meters, which was great in the mid-1980s. But it's not sufficient anymore. And as time's gone on, the Department of Defense has determined better coordinates for WGS84 and used those to re-realize its datum. That was done in 1994. And you see there it's called WGS84 G730, where G is the GPS week, week 730, which corresponds to January 2nd, 1994. And at that time it was aligned with the global frame known as ITRF 1991. This was done again in 1996, called G873, and again in 2002, called G1150. And by the time they got to G1150, there was a lot more conscious effort on the part of the DoD to really, truly align these things with the International Terrestrial Reference Frame, the civilian reference frame. And that's even more the case now. There's been a new realization in February 2012 called 1674. It's aligned with ITRF 2008 at EPIC 2005.00. So it's all very consistent. But an important thing to note is that 2005 is not the same as 2010, which is the epoch for NAD83, and that 5-year difference causes some complicated issues to arise, which I'll hit. But right now, I'm supposed to stop when we answer questions, and also there's beeping in my ear, and I don't know what it means.
Okay. Hey, Bethany, we okay? I hear that beeping too, but are we okay?
Our audio's line seems to be working fine, and we are troubleshooting. It seems like our issue right now may be mostly with our folks on Internet Explorer. So we are still looking into that. If we want to take some questions.
Okay, so we can go ahead and so actually, Michael, I have a question. So when it transitioned from WGS84 G1150 and then went to G1674, the actual difference between those two, I guess if you boil it down to accuracy, was not that much, right?
No, it's not much. It's not much.
And then but the epoch date ends up being, I guess, fairly significant, because if you're in, for example, Hawaii, where it's moving 4 centimeters a year, 5 centimeters a year, or something like that, then if you're talking 4 years, then that's 16 to 20 centimeters of movement, something like that. Yeah,
that's right, Eric. So the coordinates themselves, if you put them to a common epoch date between the two realizations, you're talking a few centimeters. It's really the tectonic motion that matters. And in addition to the difference between 2001 and 2005 on the slide, is the DoD annually updates the coordinates transmitted by the satellites to account for tectonic motion. So right now, the satellites are transmitting positions corresponding to an epoch of 2013.5. They do it at the midpoint of the year, each year.
Okay.
So they're actually updated to the current tectonic positions.
Okay. But that's just if you're taking raw, I guess, GPS measurements without any kind of correction, right? So if I was using an RTK network or WAS or some other kind of reference station, it's going to be referenced to whatever datum and epoch date that base station is referenced to, correct?
That's right. That's right.
Okay.
It only affects you for autonomous things, which would include point PPP, precise point positioning.
Right. Interesting. Okay. Any thoughts on this, Kevin?
Yeah, sure. One of the things that our users would have to remember is, like Michael said, if you are, especially in the GIS world, if you are surveying or collecting information with in WGS84 and you're getting this WGS84 realization G1674 at, we'll call it essentially your epoch of date because it's mid-year, so if you're working this year's the middle of 2012, if that's not the final reference frame that you want to work in or datum that you want to work in, there's quite a bit of tectonic motion as well as a datum transformation that has to be applied to get you to, say, some local datum like NAD83. So as Michael had said before, WGS84 and NAD83 drift apart, and they're just simply not the same. And it could be quite a bit of difference. It could be much more than just a few centimeters that we had just mentioned.
And so I guess you could say that WGS84 and ITRF, the latest realizations of both, how closely are they aligned, just to be clear?
Okay, they are, sorry, my computer screen went out. The official construction of the datum transformations is they are identical. It's officially defined as zero difference. In reality, because it's different techniques, there are residual differences, but by construction, there is no difference, if that makes sense.
Right. So the challenge, and I've seen this many times, is someone will bring up let's say some imagery in their GIS, and they say it's referenced to WGS84, but boy, that can mean a lot of different things, right?
Yes, that's right.
Yep.
Certainly can.
So I want to jump in here now, if you don't mind.
Sure.
It looks like we may have solved some of the issue. I want to recommend to our audience if they have Firefox, it looks like that is working best for us at this point. You may need to log out, log back in, or refresh your screen to catch up to the slides at this point. We seem to have solved the beeping on the audio line that only some folks were hearing, not everyone. So I hope that we have solved this issue, and I apologize for the inconvenience. I just wanted to let everybody know that if they do continue to experience issues, please let us know. But we are going to continue with the presentation here in a moment.
Okay. So also this is a record event too, and so if you are having issues with the display of the slides, you can always download it later and go through those and hear the audio too. So I'm going to go ahead and Michael, if that's okay with you, should I go ahead and display the next slide?
Yeah, let's do it so we can look at some of these look at these transformations now.
All right. So I just displayed the next slide.
Okay. All right. So here's what's going to happen. I have a series of 4 slides which are maps of the coterminous United States, and there's contours on them. And the contours represent the difference between this thing called WGS 84 and this other thing called NAD 83, the horizontal difference in feet. Apologies to people who are metric out there. So here's what you see. Now this particular map, and there's 4 of them, they're all of the same thing, ostensibly, WGS 84 and NAD 83. And it gets pretty confusing. Now the one I have up here at the moment is the one that essentially all commercial geospatial software does. If you tell it you have NAD 83 2011 and you tell it to go to WGS 84 and vice versa, it will do the transformation you see on here. Okay, and as I said, you'll start seeing differences. Now, what's going on? In the background, all the software is using a 7-parameter Helmert transformation. So it's based on a 14-parameter, and without getting to the gobbledygook, half those parameters are for the velocity, essentially the rate of change between the datum definitions. So if I only do 7, that means the difference is based on the reference time of the definitions themselves, and the reference time is 1997.0. So that's what you're seeing is the difference between these 2 datums at 1997.0. That's just how it works because all the commercial software at this time ignores that time-dependent part. So, I mean, it's kind of a drag. It means it's not right, but how much it matters to you, I guess I couldn't say for sure. That we really would get into the weeds on that. So instead of worrying about applications, what I'm going to do instead is go through the next slides. And before I know there's some delay, so before I do it, let me just say this. There's some things we already know from our conversation, and maybe you already knew before you got into this presentation. One of these epic dates. You probably didn't know about 1997. That's just a reference time by convention. The other one we have seen is 2010.0. That's the epic for NAD 83, the current epic. Another one we've seen is 2005.0, which is the current epic, or the epic used to define WGS 84 and ITRF and IGS 08, and those are all those 3 are pretty much the same thing. So I have these different dates. Now what you could do if we got more sophisticated is say, well, why not use all 14 parameters, right? If I use all 14 parameters, then I can include this epic date and get a more realistic transformation. So Eric, when you advance the slide, everybody can watch the contours change. Go ahead and do that.
Okay. I'm going to do that now. Okay.
Okay, they all shifted by some amount. You see the 4.5-foot contour now is moved in from the Pacific into Central California. 4 foot's moved from Arizona into New Mexico, etc. It's all kind of shifted. The magnitudes have increased. What I did is used a 14 parameter with an epic date of 2010, and it's the same epic date for both. I just applied it, and it created these contours. Okay, and they're all nice. One thing you'll see is they're all nice and smooth and pretty. Everything's very clean, the way it ought to be. Now, there's a problem, though. This is epic 2010, but we know that the WGS 84 is epic 2005, at least the published coordinates, if I can say that. So I can say, well, wait a second. What if I use 2005 instead? What kind of contours will I get? Go ahead and advance the slide again.
Okay, I just advanced it.
Okay, now they all kind of shifted back the other way. 4 foot contours going through Arizona again. 4.5-foot one's gone off the screen. It's out there in the Pacific. So this one actually is the closest you can get with a 14 parameter to the quote-unquote correct transformation. So if you used a full-blown 14-parameter transformation and said you're going to use time 2005.0, this is what you would get. But there's a problem, and this is an unfortunate complexity that I'm not sure what to say about that right now, but it's a complexity that's about to occur. That difference from 2005 to 2010, that 5-year difference, what we have to do to account for that is model the differential plate tectonic motion in that 5-year period. And when you do that, you correctly perform the transformation, which is the messy one. And before you advance it, though, everybody, I guess you can kind of eyeball that 4-foot contour. You'll see that it doesn't move very much, but some interesting things start to happen about there and to the west. So go ahead, Eric.
Okay, I just displayed the next slide.
Okay, there you go. So everybody can see what's happening, right? You can see the San Andreas fault system, really, in California, and things changing dramatically once you hit that. The 4-foot contour just gets cut off at the in Cia Cortez. And also you see big changes in the Pacific Northwest, a lot of tectonic activity. That's what you're seeing. And so we have this huge difference between these very complex differences between the datums. And this is the correct transformation between the two datums, but it's very complicated because of differential tectonic motion. I have to be careful what I say here because I don't want to besmirch the agency I work for in any way. There are reasons for doing what we did. We used 2005 as the epic date for IGS 08, which is the same as WGS 84, which is the same as ITRF 2008, because that's the worldwide convention. 2005.0 is the epic date. And we used 2010 for NAT83 to have something more current. But that caused this complication to occur. Had we used 2005 for both, all the contours would have been, as in the previous slide, very nice and smooth and very simple, and you could do the whole thing with a simple 14-parameter transformation. But now we have this situation, and the differences can be large. Oh, go ahead, Eric.
Okay, I'm going to ask you to sort of zip through these if you can, even though they're important.
Okay, I'm done now. I think this is second to last slide. So does it really matter? Well, once you get down to axes of better than about 2 meters, it starts to become a problem, right? Because that's the magnitude of these kinds of shifts. So depends on what you're doing, but just be careful, as it's come up before, when you use WGS 84. If you do, understand what kind of accuracy you're trying to achieve, at what epoch, and what realization. There is no just plain WGS 84. And things are moving, so it can make a difference. I've got an example that I like here for Hawaii. It's moving about 7 centimeters per year west-northwest in WGS 84. It's moving 8 centimeters per year northwest with respect to North America, but only 4 millimeters per year with respect to the Pacific Plate, and that was by design. So modern GNSS is becoming more precise. Soon autonomous positions will be better than the 1 meter, and this becomes more complicated. Accuracy, so things are very precise, but accuracy is a whole different issue, and when you ask about accuracy, it's with respect to what? And one more slide.
Yep, there you go.
Okay, now it's come up for me. So this is just showing that globe again and just throwing up some little quotes I got from Dave Doyle, so I'm using them because I love them. Geography without geodesy is a felony, punishable by imprisonment without trial. And good coordination begins with good coordinates. Thank you very much.
Hey, thanks, Michael. So I'd like to go ahead and display the second poll question. And so the question is, in managing its geospatial data, does your organization account for the epic date of the data? Answers are yes, no, we were just starting to think about this, or I don't know. And like Michael said, it can make a huge difference. I mean, if you're talking about, a coordinate with an epic date of 1997 versus one with an epic date of 2013, that's what, 16 years of plate movement. And when you're talking about a few centimeters or even a decimeter accuracy, I mean, it's significant. So I'm going to go ahead and display the poll results, which is about what I thought. Doesn't surprise me. And by the way, what I'll do is in the fall newsletter, I will publish the final results as well as the number of people who had voted, so I'll be able to understand the statistical significance. Moving on, I'd like to go ahead and pass it on to Kevin Kelly of ESRI and for his presentation. Kevin?
Thanks very much, Eric. Thanks, everyone, for joining us today. I'd like to thank Eric for staging the discussion and letting me talk about how ESRI is working towards providing some solutions for our users to these problems. We're not there yet, but we are progressing. And thanks, Mike, for your excellent layman's primer into that world of horizontal datums, velocities, and the challenges that the community faces. First thing I'd like to do is divorce this challenge from this implied connotation of high accuracy data. Mike mentioned this just at a couple of slides ago, and it was great, that this is a qualifier that may serve to divide users into two camps, the so-called high accuracy users and then everyone else. So introducing that same division that Michael made that may be surprising to some GIS users, although I don't quote any hard numbers here, I'll propose that this issue is relevant to any GIS data capture operation that collects data using GNSS technology, even at the 1 to 2 meter level, much less those collecting GIS data at sub-meter to sub-centimeter level. So considering that, this terminology, high accuracy, now becomes somewhat fuzzy. Next slide.
Okay, displayed.
Currently, ESRI technology correctly performs transformations between what I'll call classical geodetic datums only. Datums essentially that remain static in time. We call these geographic coordinate systems, or GeoGS, or GCS for short, as I'll use throughout the presentation. Now, these transforms are generally unique, they're closed form mathematically, and they're invertible. There are at times maybe some ambiguity in selecting the right transformation from a set that purports to transform between the same two geodetic datums, but some new functionality at our 10.1 release defining area of applicability of transformations has simplified this problem to some extent. But now once we open the door to time-variant geodetic datums, well, a host of thorny issues arise. Regarding some of these, you're going to hear a lot of questions that I'm going to pose, but I won't really be able to give any hard answers. That's because these questions, they represent the challenges that we're facing, or the challenges we have to resolve to design a robust and correct functionality to handle this kind of a problem. Next slide, Eric.
All right, here it is.
Time-dependent geodetic datums, or reference frames, are not currently defined in ESRI technology. Our current thinking here is possibly to create a new entity that is perhaps a time-enabled GCS, similar to our time-enabled feature classes. But these kinds of time-variant reference frames, as Michael so clearly showed us, now form the basis for most national geodetic datums worldwide, and certainly the datum basis for all GNSS systems out there. The time element for these transformations enters through the need to maintain the stability of these reference axes, the stability of these frames by modeling their time evolution. Now, also, since physical location of features move measurably with the crust due to tectonic plate and local crustal motion, clearly these coordinates and the coordinates of those features change measurably with time. And the positional shifts can be quite significant, in some cases amounting to many centimeters per year, as Michael showed, not to mention meters of near instantaneous displacement sometimes due to episodic events such as earthquakes. So coordinate changes of these magnitudes simply can't be ignored in the GIS systems. Next slide. This is just a short list, a brief representation of the applications of reference frames to geodetic datums or adopted national geodetic datums around the world, and almost as well as worldwide GNSSs, all the different GNSS systems out there. I only mention a few here. This is, as I say, a short list. This can be multiplied by many, many times for any national geodetic datum currently, any country that has a national geodetic datum. So we can see that most, if not all of these, well, in this particular case, all of these datums are referenced to what we call the ITRF, which Michael mentioned, and this is a three-dimensional Cartesian coordinate system that is involved with these kinds of time-dependent situations. Next slide.
Okay, I pushed it out.
So essentially, coordinates move. In a nutshell, we have two similar-looking but vastly different geodetic problems here that we have to address in software. The first, and what I'd like to say is the simpler of the two, Michael might argue with me on that one, but that represents the time-dependent three-dimensional Cartesian coordinate transformation. Now, it can be viewed as a datum transformation, although, strictly geodetically speaking, sometimes it is and sometimes it's not. For example, the WGS84 to NAD83 transformation, which we just saw a lot about, is a datum transformation. But, for example, ITRF 2000 to ITRF 2008 is not, even though the mathematics is exactly the same in both cases. We'll push that off as a discussion perhaps for the purists, but we will call these synonymously a reference frame or a datum transformation. It's time-dependent by virtue of the time evolution of its transformation parameters, and that's represented mathematically by their time derivatives. Now, these time derivatives must be incorporated into the transformation, and so that intrinsically imposes a requirement that the data being transformed is time-tagged. The second problem, shifting coordinates within the same reference frame, sounds simple, but it's really rather extremely complex, at least from the software perspective. The complexity arises from the requirement to apply empirical models to estimate displacements due to one or all of global tectonic plate motion, local crustal motion, that's usually most pronounced along the boundaries of two or more tectonic plates, and certainly positional shifts due to episodic events such as earthquakes, volcanoes, and landslides. All these are typically modelable and can be handled in a context like GIS. But these models are complex, they're continuously changing, and they're typically non-standard in their format and non-standard in their implementation. Next slide.
Kevin, while you're moving slides here, I just wanted to cut in and see we are having a little bit of audio difficulty. One moment, and allow me to troubleshoot this as well.
Sure.
Okay. All right. We are going to, again, look into this audio issue. In the meantime, if we could just speak up a little bit as we present, and we will carry on with a few more slides here and see if we can work this out.
Very good. Kevin, is the right slide out there for you, the implementations challenge?
Are we about ready to go?
Yeah, I'd say go ahead and push forward on it. It should be recorded okay, so we'll be okay, I think.
Okay, I'll carry on, Bethany.
We appear to be having a system-wide issue with our webinar provider, so we're taking a momentary pause here on the audio.
Okay.
Okay.
At this point, Eric, let's queue up the last slide with everyone's contact information, just so that people can have a chance to take down those email addresses while we have this moment pause.
Okay, I just displayed that slide with all the contact info. Kevin, just to be sure, we were on the implementation challenges slide, right? That's the one you went up, right?
Currently, yeah, correct, Eric. Implementation challenges is where we were.
Okay.
Well, we've partially resolved the issue here, and we do have audio backup. We do have a beeping sound again that's going to be heard by some of you folks, and we are looking into that right now. But Eric, we can continue the presentation since not everyone is hearing this beeping sound that I know our presenters are probably hearing right now.
Okay. All right. So I just displayed the implementation challenges. So
Okay, implementation challenges. Okay, from the GIS perspective. Now, technically, one could say here that there really is no problem. All the mathematics, all the models, all the data, they're all there and they're ready to be applied. But implementation in a general GIS software such as ESRI technology, well, this presents some tough problems. Now, depending on how we would build this functionality, we could shift most of the implementation problems to the user, the easier and that may be the preferred option, or we could attempt to automate the processes, kind of much like our current on-the-fly transformation functions. But this approach brings on many difficult problems such as data management, housekeeping, if you will, generalization, processing rules, standard parameters, and so on, processing workflow, whether we do this on the fly or user-driven. Now, I'm going to attempt to highlight these with a couple of very simple examples. These won't be exhaustive examples, but they'll just help you to appreciate some of the challenges that we face here in being able to implement this in software. Next slide, Eric.
Okay, I just displayed it.
Okay, here's one problem from the software viewpoint. Now, generally, features are collected all the time, and they're collected at arbitrary epochs. So suppose features are collected in a particular time-dependent reference frame, say we'll call it GCSA at epoch 1, and then suppose those same features or even new features are surveyed again later at epoch 2. Now, simply merging the two data sets will or may present a positional disparity, but depending upon the duration between epoch 1 and epoch 2, and depending on whether the two reference frames were the same. Now, how should the GIS reference or distinguish the two data sets? Are the GCSs the same or are they different? Now, if they're the same, well then, how can the coordinates differ? Remember, from the software perspective, they're the same GCS, but different coordinates, same feature. So if they're different, well then we can end up with a unique geographic coordinate system at every epoch. And that can end up being a lot of GCSs. Now, if we tag the feature with an epoch, then potentially we could end up with a unique feature for every epoch. And that can be a lot of feature representations for the same feature. So either way, we somehow have to keep track of how to move between epoch-tagged GCSs or epoch-tagged features. We clearly need some rules, perhaps, to limit the number of GCSs from multiplying ad infinitum. So we have to consider time-tagged features, time-tagged geographic reference systems, geographic coordinate systems, or time-tagged features and time-tagged GCSs. And then we have to manage them efficiently. Next slide, Art.
Okay, just displayed it.
Here's a problem for rule-based processing. Here we have two methods. We won't discuss at the moment whether these two methods are equivalent or not, but two methods of getting data from frame A to frame B. Which one is the standard method? Which one would be the one that we ought to implement in software? The method of choice here may depend on which model has an associated velocity model, noted here by the VM in the oval, but what if they both have velocity models? Regarding epoch dates, are all epochs valid, or are only certain epochs valid? Does each reference frame have its own unique valid epochs? You know, and many do, but people are collecting data at all epochs, so how do we deal with that? What about the plate motion and the local crustal motion models? These models have to be specific to a particular reference frame. Local models change often, and they certainly change with every earthquake that occurs. And of course, these are the regions where the models are most important and they're most applicable to GIS data. So for example, for on-the-fly transformations, we would need rules regarding methodologies to be used, standard epochs, standard crustal motion velocity models and displacement models. This may work well for well-known transformations like WGS 84 to NAT 83, but without these rules, the process would have to be a manual, user-driven geoprocessing type application. But if we had such a user-driven process, of course, that brings flexibility, but then its complexity limits its use to knowledgeable practitioners only. Next slide, Eric.
Okay, it's displayed.
Okay, now thanks, Eric. This is my last slide. We have other issues to consider too. What about this idea of multiple transformation parameters between the same or similar reference frames? Well, this point seems kind of obvious. We'll just use the parameter set corresponding to your source data. But this isn't always followed or easy to determine in practice. For example, loosely speaking, NGS considers ITRF 2000, IGS 2000, and IGB 2000 to be equivalent reference frames in their HTTP software from the transformation perspective. Now that could be confusing to a non-specialist using software such as ours if we don't deal with it somehow. Velocity and plate motion models, they have to have hard geographic boundaries. Are those geographic boundaries standard? Do they change over time? How would we reconcile data sets operated on when the velocity model has changing boundaries, when their boundaries change? We will certainly have performance issues with the point and polygon requirement. Every single point has to belong to a plate model or a particular velocity model. They may be hierarchical, and we have to check every single point that we transform to find out which plate model it belongs to, and that becomes a problem when we want to transform thousands, even millions of points. Handling discontinuities along fault or plate boundaries where an earthquake has occurred. This is also something that is surely data falls there. We have to deal with it somehow. So this is just throwing out some ideas for you to appreciate how difficult the problem is from implementation in a software perspective. From a software perspective, it's not simple, and it requires great care in the extent to which we simplify and generalize these processes. And these are just a couple of the challenges we face implementing this in ESRI products. But there's one challenge that trumps all these that I've mentioned so far, and that challenge only begins after we have fully developed all this functionality and put it out there. And that challenge is educating the users. Thanks very much. Back to you, Eric.
Hey, thanks, Kevin. That's a great presentation. I'm going to ask another poll, or publish another poll out here, ask a question. I just displayed it right now. It's do you know where to access local survey mark information for you to check accuracy? So in other words, do you have a resource of some kind, probably a government agency, that you know how to access, so you can find a survey mark nearby you where you can go occupy that with a high precision GNSS receiver or some method of using that to truth your geospatial data. And just another note here, even though we're in 57 minutes into the webinar, I mentioned at the beginning that we can go up to 90 minutes, and so Craig's his presentation is still up. We'll still take some audience questions, so if you want to hang on, that'd be great. We'll probably go to an hour and 15, hour and 20 minutes or somewhere around there. But go ahead and answer the poll question, and then I'll display the results here. And that's actually great news. For those of you who don't know where to access, boy, feel free to shoot myself or one of the panel members a question and say, hey, here's where I'm located. What's the best local source I can use to find survey marks where I can truth my geospatial data or my GNSS receiver? And again, I'll publish the complete results of this poll question in a follow-up newsletter. Now I'd like to introduce Craig Greenwald, Technical Director at GeoMobile Innovations. And I introduced Craig in the beginning, but again, I worked with Craig a number of years back. He's very knowledgeable on GNSS and mobile GIS, and was on the ESRI ArcPad team for a number of years. And so I'll go ahead and pass it on to you, Craig.
Thanks, Eric. So, so given all this excellent and detailed information that that Michael and Kevin have given us, what's a user to do? Basically, I've got to digest all this as a user and make some decisions when I go out there and collect or update coordinates in the field using my submeter or more commonly these days my subfoot or decimeter GPS GNSS systems. So when preparing for going out there and doing high accuracy and even as Kevin said, you can consider even 1 to 2 meter GPS now GNSS as high accuracy. data collection. So there's a couple questions that I ask myself when I go out to do these data collection sessions or prepare for data updates. First of all, what's the datum of my base map data, my background data, and more importantly, what's the datum of my operational data, the data that I'm actually going to be collecting or updating out in the field. And I get the datum, but also what's important and often unknown, as Kevin and Michael were alluding to, is the epoch. When was this data transformed? Using what method, what epoch? How stale is the transformation? Essentially, was this data surveyed in using techniques where we're working off of a base station, working off of a control point that's been adjusted based on the latest epoch, or is this data that was transformed from NAD 27 to NAD 83, and then from NAD 83 original to NAD 83 Harn? What's the kind of legacy of this data? And generally, we don't know. That's the reality of it. We just don't know. And to me, the background data isn't really important. In most cases, I'm not looking for that warm, fuzzy feeling of the data that I collect lining up with my background data as much as I am with doing it as correct as possible for collecting this new data, and then we can sort that out moving forward. The background data is legacy; it's background. So when I'm going to collect new data, the question I'm asking myself is, one, am I only collecting new data, or am I updating an existing data set? Am I updating features in that data set, basically moving them to their correct coordinates? Maybe they were originally digitized or hand-entered off of a Garmin recreational unit, or am I adding new features to that data set? Or am I just creating a brand new data set, something that's never been collected for, that I'm bringing into my GIS? And I might make different decisions based on that. If oftentimes if I'm collecting brand new data, I will do the approach of basically collecting WGS84. Now again, Kevin made a point, and Michael also, about there's WGS84 or ITRF current. It's basically moving in time. So WGS84 today is not WGS84 6 months from now, and a year from now there's this slight movement. And since there is no epic tagging of feature by feature or data set by data set, point by point, what do we do? So to me, the best practice is, based on what we have today, is if I can collect new data and there's no existing datum that I'm working with, I will collect in WGS84 so that at least I minimize what the software is doing. I know that the software itself has not done anything to transform that data before I bring it back in desktop. Because my world, again, is the field world. I'm out there in field software, generally ArcPad or ArcGIS mobile. So if I'm going to do a zero transformation, that's one approach. I need to make sure that the software is indeed doing that zero transformation. I've decided, am I going to make that transformation either in the field or the desktop? And then if I am going to let the field software do my transformation, let's say I know I'm working in NAD 83 data and I've got to collect into that NAD 83 existing data set, which transformation do I use? ESRI has a whole bunch, dozens literally, of NAD 83 to WGS 84 transformations. And there's a lot of them that are actually the same transformation, just with different names, in order to match things in your PRJ file. Basically, I've got a list here in front of me. It's not on the screen anywhere, but there's basically 4 overall transformations that are used in continental U.S. between NAD 83 and WGS 84. And again, they have different names, but there's 4 basic ones. One of them is a zero transformation. This is where Michael was saying that originally NAD 83 and WGS 84 were considered the same. So the transformation in that case would be a zero transformation. The one that I've been using lately, it's the latest one. It's the ITRF 08 to NAD 83 2011. That's kind of the latest one that is in ArcGIS. I think it appeared in 10.1. It's not yet in ArcPad, but it should be there in 10.2, which is in beta. We can go to the next slide.
Hey, just Craig, this is Eric. Really quick, you can create your own custom transformation within any of those ESRI platforms, right?
Yeah,
if the
actually,
if the latest one is not there, then, and for example, if they're using 10.0 or 10.1, they could create their own transformation in those legacy versions, right?
Yeah, that's a good point, because that one that I was just talking about, the ITRF 08 to NAT83 2011, I've been working with that one now for the last, about the last year or so, and that's even with my 9.3 or 10.0 customers, ArcGIS Desktop, and also since it's not yet in ArcPad, I do that in ArcPad as well. And what I've done is I've gone there and I've defined those parameters that ESRI's provided and put them in myself, so that ArcPad is using them, and they're set up in ArcGIS Desktop. So ArcGIS Desktop will use them for on the fly or for fixed transformations, and ArcGIS for mobile will use them based on the data frame when I publish it out. And that kind of leads into the slide that's up there right now, that there's different transformation workflows that I have to use in each of ESRI's products, depending on how, which one I'm using to collect data in the field and to bring that data back into the office. So, in ArcGIS Desktop, now we're basically talking about data that's been collected in the field and is then brought in the desktop. What do we do with it now? If, we've got geoprocessing tools to transform data. We've got the project data tool, which I use all the time. And so once data comes in the field, if I know it's been collected using WGS84 and now I want to bring it into NAT83 to match my maybe other data sets that didn't come out in the field, I would use the project data and make sure that when I choose the transform, either way the software is going to ask me which transform you want to use, I'm going to use that latest one that I've manually entered in previous to 10.1 or that will be there in 10.1 and later. Or I might just let ArcGIS Desktop do on-the-fly transform and keep that field data in WGS84 until I'm ready to do something else with it. And in that case, again, I want to make sure that I'm telling the data frame which datum transform to use. When I get into the ArcPad world, what ArcPad does is it's automatically in the background doing an on-the-fly transform for you between the incoming GPS datum and the datum of your map data. So in general, ArcPad doesn't do on-the-fly of actual map data, just of your GPS. So all your data is going to be in the same coordinate system, same datum. So in the example where your field data is in NAT83, behind the scenes, ArcPad is transforming that incoming GPS coordinates from WGS84 to NAT83 for you. Now, which transform is it using? That's kind of the crux of the issue. You need to understand that. So ArcPad will pick a default, and really, unless you change that, it's kind of up to you to verify that default is correct or the correct one you want to use. And if not, you need to go and change it. ArcPad kind of hides this in a sense in this tool called the Datum Configuration tool. So this is a desktop tool. You can look up some of the help on it, and you can use that tool to go ahead and figure out what transform ArcPad's using and tell it to use a different one. And just as an FYI, what ArcPad's using right now is the equivalent of the ITRF 94 to NAT83 Cores 96 transform. That's the _5 transform for those of you who are familiar. So this is rather old. There's about 20 years of plate movement has occurred since that transform, basically since the epic dates of that transform. So you may not want to be using that, or you generally don't want to be using that when collecting new data. In ArcGIS for mobile, what the approach is, it's slightly different. There's also an on-the-fly transform, but you don't really have control of this in the field software. And ArcGIS for mobile, it's hardwired that it's always assuming the incoming GPS is WGS84. We'll see in a minute in another slide or so. We'll see that it might not. Your incoming GPS might not be WGS84. It generally is, but there are some cases where it's not. So ArcGIS for mobile is always assuming that. And the transform on to the map datum, it's based on what datum transform you've defined in the data frame in ArcGIS Desktop when you publish the data. So going back again to the ArcGIS Desktop workflow, you want to make sure that you've chosen the datum transform that you want to use in Desktop to go between WGS84 and the datum of your data, NAT83 in this case, and make sure you choose the one you want, because that's what ArcGIS Mobile is going to use. Next slide.
Yeah, this is Eric. Just one comment on that before we leave this slide is that there's been some frustration among ESRI users that ArcGIS for mobile and ArcPad have substantially different datum transformation, I guess, configurations or capabilities, I should say, right? I would say that probably ArcPad has a bit more advanced capabilities in this area than ArcGIS for mobile does. And Craig actually worked with me on a project in the past 6 months or so where a large enterprise organization was deploying ArcGIS for mobile in the field and trying to use RTK network data with the high precision GNSS receiver that's coming in as NAT83. And it was a bit of a challenge. It wasn't certainly a point and click sort of thing to pick the right transformation. I think we ended up having to design a custom transformation to be able to make that work.
Yeah, absolutely. And actually, it reminds me of something I meant to mention in the previous, is that when a lot of times what you wind up doing is you wind up tricking the software to do a zero transformation, is that you basically lie to the software and you tell it that your map datum is the same as your GPS datum so that it doesn't do any kind of transformation. So in that case, and again, the approach was different for ArcGIS for mobile, where in that case you'd have to basically tell the data frame to use a zero transform versus ArcPad, where you just need to tag the PRJ file of the data that it is basically that it's, or tell ArcPad that the GPS datum is NAT83 so that it doesn't do the transform. So very confusing, and really where going to survey points to double check this stuff before you start a big collection project really helps tease out what's going on there.
I've even had users. I'm sorry. I've even had users use a free off-the-shelf software that just records the raw NEMA data coming out of a GPS receiver, just so they take out any kind of variable, any kind of datum transformation that certain software, it could be ArcPad or something else, is doing, so you can sort of try to dissect the problem of mismatched datums by removing these types of variables, because a lot of times it's not easy to know what ArcPad or ArcGIS Mobile is doing. Craig, I've displayed the next slide for you.
Yeah. I mean, that's another reason why. Oh, go ahead, Kevin.
Yeah, I just wanted to mention that the ArcPad and the ArcGIS Mobile workflows, I think the reasons why we're having these types of issues is because of the design criteria for both of those products, and the design was that we would be collecting something I don't like at all, GIS grade data, which I don't believe there's any such thing, but that's the terminology that has been out there, at the meter level, at the couple of meter level. And the idea was that, centimeter level data or maybe even 10, 20 centimeter level data, it wasn't really what the intention of how that product was designed, but now they're realizing that that kind of information is very prevalent, and they have to catch up a little bit with creating the proper interfaces for transformations.
And that's also.
Sorry, I'd just like to comment on that. I appreciate Kevin coming out here and talking about this, because Esri's sort of the big elephant in the room, and I think they're a driving force behind how we can bring this whole issue to light and improve the workflows and account for this increase in accuracy of data. Go ahead, Craig.
Yeah, and all this is another reason why I strive to use the zero transformation as often as I can in the field, whether it's applying a zero transformation, whether it's collecting data in WGS84 or just tricking the software not to do any transform, because then at least I pull that out of the equation. I could take my time back in desktop and make more informed decisions, call a meeting, do what needs to be done before the data then gets transformed into the datum of my GIS, the data sets that I'm working with day to day. So along those lines, on the current slide, you can see what we were talking about was different sources of GPS data or corrected GPS data will give us different datums. So most of the time these days I've been in a real-time workflow. It's kind of post-processing is becoming more and more of a corner case. Certain agencies have to do it. Certain agencies still do it for various reasons. But just be aware when you post-process, regardless of what datum transform you've defined in the software, if you're using a package that post-processes the data and then brings it back into your GIS, it's being transformed. It's being transformed against the base. The underlying data is transformed against the base station's datum as defined. So you're relying on, and most of them are good, but again, you're relying on that base station to correctly have done its transform from how it's published and over different epochs to current what's coming in from GPS. So there could be, again, 10, 20 years sometimes of movement, crustal movement, and the coordinates of the base station may or may not be updated. You need to know your base station. But again, in the real-time workflow, where I'm mostly working in, then what you need to do is look at what's the source of your real-time corrections. So if you're using, in the U.S., WAS, which is a type of SBAS, in the U.S. it's using ITRF-08. So it's basically in line with the GPS datum. So the WAS corrected data, the GPS data, it's all the same datum coming in. You could treat it the same. When you get into RTK type stuff like VRS and whatnot, you really need to check with the source of your data. I know here in Oregon, the one that we use that comes out, I think ODOT manages it, they just went through a change where they just were upgrading. We're moving things from 93, 2007 to 2011. And so during that time, there were warnings out. If you collect data during this time, you may have a shift. If you start the data collection today and then the shift happens tomorrow or next week, you need to be aware of that kind of stuff and don't just plug into your VRS system and then be plug and play from then on. Be proactive and know when these things are changing, and also what the source is as you move around to different places and use different sources. I know here in the U.S., the Coast Guard beacon, not too many people still use that, but that's also often a source of confusion and datum shift because it's based on NAD 83, the CORS 96 2002 epoch. So again, you need to trick the software and tell the software, hey, my incoming GPS datum is NAD 83, so that it doesn't transform to your NAD 83. Otherwise, you can get a double transform in ArcPad or ArcGIS for mobile if you're not careful. And then there's other ones like commercial ones like OmniStar. I know OmniStar is different depending on where you are. In the U.S., it's based on, I believe, NAD 8386, so the old NAD 83, whereas international, it's based on the GPS datum, ITRF. You're right. So the lesson here is just when you're doing real-time corrections, just like when you're doing datum transforms, when you know what the datum is, you need to make sure that there's not an extra transform sneaking in or a transform that needs to occur being avoided. Next slide.
Okay, it's displayed.
Yep. And then just some kind of notes here on field testing this stuff so you get that warm fuzzy feeling and you know that what you're actually out there collecting is correct, correct given all these other caveats that we've talked about. I like to go out there and do an accuracy test, but also a precision test. And so just so we know the difference, these are terms that I throw around, but a lot of people use them interchangeably. Accuracy is the difference between what you're measuring out there in the field and truth, right? What is truth? Generally, it's a survey mark. But again, truth changes over time. And then precision, we're just talking about relative changes. So that's if I stand in the same place and capture a static line, how far does that line move around? Does it all kind of stay around within the same place? And where precision comes into play is that if I'm just doing area or line measurements, I'm getting basically distances and areas, I'm not that really concerned about epochs and stuff like that because everything relative, as long as I'm not working right on a plate boundary, I'm working within a plate, then everything's going to be relative to itself today when I'm collecting the data. So, if my data is off of a survey point, it looks like it's shifted off, 2 feet to the northeast consistently when I do my tests, all right, there may be some kind of epoch issue, there may be some kind of slight datum issue, but I'm not necessarily going to worry about it when I'm doing just simple area calculations or length calculations. But it's absolutely going to be key when I'm trying to dial in to get data that's accurate relative to the other data in my data set. So you always want to do this multiple times, multiple days when possible. Go out to those survey points, do it in the morning, do it in the afternoon, come back another day. Don't just rely on one set. I did have some pictures of some examples. I don't think they made them up on the slide. I guess just got one more slide to kind of drive that point in. And that is when you do go to check in on control and check against the truth, as Eric said way back at the beginning, you really want to be aware of how good are these survey marks and when were they established and how good and when were the coordinates what epoch are the coordinates tied to. So here's an example of 3 control points where I've recently done some testing. If you look at the first one, the NGS control point, that one is similar to the one that Eric showed way back at the beginning, where you can see it's based on NAT83 2011. It was adjusted June 2012. So I know this is based on basically the latest epoch of NAT83, and it's been based on GPS measurements. The key there is avoid any control points with NAT83 86 coordinates, because those are going to be optical. They haven't used GPS GNSS measurements to tie those into the reference frame. If you look at the second one, this is one I've used out in Estacada. It's near a GPS test network I test. This one was adjusted based on HARN and then some Oregon realizations of HARN, and it was last adjusted in 2000. Right, so more than a decade of movement has happened since then, across the movement. So if I go out there and everything is, I'm starting to get down to RTK or decimeter accuracy, it's something I want to be aware of, that, hey, there's going to be some movement. The last example is where we do a lot of testing under canopy. Now this, admittedly, it's under canopy. We don't expect to get better than 2 or 3 meters generally in this kind of test. It's a forestry test course, but this one in this case was last adjusted in 91. So this is one where I do precision tests. I know what the measured lengths and areas are of different loops within this network, so I can know that if those are accurate, then I've got good precision. But as far as raw accuracy, the way I consider that is, in my mind, there's like a 20 centimeter or so circle around each of these points that represents the crustal movement of, that survey mark. The truth is anywhere within that 20 centimeters, not necessarily directly at that published coordinate. And I just want to read something from an ODOT advisory that I read from the end of last year. That's what they said is that between epoch 2002 and 2010, so that's 8 years of movement, in the Willamette Valley, essentially the area where I do my work, we've got about 3.5 to 7 centimeters of movement. That's over 8 years. So if I look at something like this test network in Clackamas, we've got 21 years of movement. So, again, that's where I get that kind of 20 centimeter fuzzy circle that I think about when I do my accuracy testing. And that's pretty much what I have on my slides here.
Okay. Hey, I appreciate that, Craig. So we've got a few minutes for some questions here, and I think the one that was posed in real time in our webinar, and also I've had posed to me before, is okay. There's sort of 2 components to this datum transformation thing. It's going from one datum to another, for example, ITRF to NAT83. But the second component of that, and I think Michael and I have had this conversation before, is the epoch date. The crust, taking into account the crustal motion. And while it seems that we're sort of getting our arms around the datum transformation, it really seems like people are forgetting or don't understand how to apply the epoch date conversion to everyday surveying, mapping sort of thing. And so, and I don't know, I guess it's a question for everyone here, but I suppose, Kevin from a workflow standpoint and Michael from a technical standpoint is hey, we have to account for this epoch date and this crustal movement, because as data gets more accurate and more accurate, for example, if we're using RTK that's capable of 1 to 2 centimeters, and yet the ground is moving at 6 centimeters a year, you certainly can't ignore that. So I'll just toss it out there and let you guys run with it.
Well, hey, Eric, Michael Dennis here.
Whoops. Whoops. Who's speaking?
Go ahead, Michael.
Who was that?
I wanted to jump in anyway, because it seems like there might be, judging from some of the comments and the questions that are rolling in and that we got previously, there's some confusion on this epoch date business. So, for example, NAT83, the current realization is all on epoch date of 2010.0, so it has really nothing to do with when the observations were made. Everything has been transformed to a common time of January 1st, 2010. So every published coordinate, whether it's a CORS or a passive mark, is all at that epoch date. Now, everything's moved since then, but a vast majority of it's moved in a consistent way, so the relative positions are still essentially the same. So that epoch date business, that's a standard practice in the geodetic community to get data consistent. So some of this concern about the tectonic motion that's occurred from one year to the next is largely gone if everyone's referring to a common epoch date, and that's why we give epoch dates on our data sheets now for GPS control, so everything's consistent. And that goes to the WGS84 thing too. I saw the question, and it's a good question because it's confusing. He said, hey, you said WGS84 is at 2005, and then you said it's given coordinates at 2013.5. And both those things are right. And the deal is WGS84 coordinates are not published. I got another comment from Dave Doyle about that, which is always good to bring up with people. There's no place to go to get WGS84 coordinates. So the best thing you can do is get IGS or ITRF coordinates on, say, a CORS. Those are published at 2005.0, but the positions broadcast by the satellites are always current, and there's reasons for that. But you'd have to deal with that when you get the data. So when you get WGS84 straight from the sky, all right, it's always a current epoch. And that goes into all sorts of things that Craig talked about quite a bit, and I appreciate that. When you're getting that from the satellites, it's at the current time. But if there's been some kind of, let's say, satellite-based augmentation like WAS or other systems, OmniStar or an RTN or some other system, it almost certainly won't be at that epoch date. It'll probably be to some standard epoch date. And I am not even sure. Eric, you got a question on this answered, I think, from FAA. I think WAS does give the ITRF 2008 at epoch 2005, not at the current epoch, for example.
It's actually I clarified it with them. It's actually to 2013.5, similar to what you said.
They do that, okay.
84 is they do an annual update, and they go mid-year in advance.
Just like DoD does.
Yes.
Okay.
Yes, that's correct. That's what they told me. So.
Yeah, knowing all those things is a tricky business.
Okay. Kevin?
Yeah. Regarding the WGS84 that Michael just mentioned and the epoch date for that, Dave Doyle, of course, is correct that there is no way to get WGS84 coordinates sort of on the ground. They only come from the sky. They only come from the satellites. But according to DoD, their coordinates will always be equivalent to ITRF 08.
That's right.
So from that perspective, ITRF 08 and WGS 84 are equivalent, so you effectively have a way to access WGS 84 coordinates. That was just one comment. But what I wanted to say earlier about your comment, Eric, about the epoch date and the plate motion, part of the reason why the WGS 84 NAD 83 transformation is so large, a couple of meters, is because NAD 83 is non-geocentric, whereas WGS 84 is. Now, when you get a situation where you're working with, like the slide I put up about reference frames or national geodetic datums all being based on ITRF, all those will be geocentric datums. And so the transformation between ITRFs is very, very small. It's going to give you a very, very small differences between your coordinates. Just doing the reference frame transformation, the 14 parameters that Michael had talked about. The real shifts or the real motion comes with the tectonic motion, whether it's plate motion or local tectonic motion like we would have in California, New Zealand, Japan, places where things really move. And even in the tectonic plates over longer periods of time, but that's where you're going to really get the coordinate shifts. When you transform between two geocentric reference frames, more than likely your coordinate shifts will be very small.
So
at a common epoch date.
Yes. So I'd like to pose, so for the average user today, how do they account for this epoch date? I mean, it's not incorporated into the ESRI workflow right now, or any workflow, well, very few workflows that I'm aware of. So how would the average person, let's say if they're going out and collecting data today, how should they incorporate epoch date into their process?
Collect new data every year.
It's a challenge. I mean, it's not an easy question to answer at all.
Well, the challenge comes from the fact that there's very few tools out there to handle it.
Yeah.
If you're collecting a lot of data, and you want a tool out there that's going to take your data and correctly deal with the epoch date, and you just don't, you come up empty. ESRI, of course, is working towards this, but it takes time. With respect to all the challenges that I'd mentioned, it's not easy. Our software is large, so it's difficult sometimes. HTTP through NGS is available. It's just that you have to go through the pain of getting your data in a way that HTTP can handle.
Yeah, that's the challenge. I mean, if you think about it, if I was a enterprise organization, and I'll go back to my utility company example, and I'm collecting thousands and thousands of points per week or per month, somehow I want to time tag those so I can have them all on a common epoch date when I have them in a GIS, and whether it's 2010 or whatever. But there's a lot to be said for having a fixed epoch date like what Michael talked about. I mean, just because it says 2010 doesn't mean it's collected in 2010, but you need to reconcile it from today back to 2010 to take into account the plate movement.
Yeah, and that's the real trick, is knowing what you have.
One of my colleagues just came in, and I should have known this because I figured this out some time back. Well, it doesn't take much to figure it out. One of the ways that users could currently, even with ESRI software, handle this problem is to make a custom transformation, take a 14-parameter transformation model or equations, and turn it into 7 parameters, which can be done if you have your epoch dates, and then use that in ESRI software to do a 7-parameter transformation, which really hidden in there really is 14 parameters, but it's going to be unique for each data set that you want to transform, and you'll have to do it yourself for each one. But that can be done.
Well, on a clarification on that, though, that won't work if the epoch date from one is different from the epoch date to another. For example, that won't work to go from IGS 08
to...
Exactly. That's a huge point of confusion with people. Exactly. So, in other words, you can't go from IGS to the published course coordinates on IGS to the published course coordinates in NADD3 with that method. So that's kind of the drag.
It won't work for crustal motion, but it gets you better than what you currently have now in ESRI software.
Well, very good, folks. I mean, we could probably talk another hour on this subject, but we probably ought to wrap it up here. We're 92 minutes into it, and there's lots to discuss here. And this won't be the last webinar dealing with this subject. So I'd like to thank all the panel members and the audience for hanging in there. I mean, we've still got a strong audience even after 90 minutes, so I appreciate that. And thanks, guys, for hanging out here with me. Bethany, back to you.
Well, first of all, thank you to our speakers, and again, thank you to our sponsor, Hemisphere. Most of all, thank you to all of our dedicated, engaged audience members for sticking with us here today. It's truly a testament to the importance of this topic that we're continuing to receive your questions on this presentation. We really appreciate your patience throughout our technical difficulties today, and I'm going to personally email all of our attendees a download of the slides with our speakers' contact information this week in case you've missed anything. You will also receive the link to the on-demand recording of this event in 2 weeks emailed to you. And finally, that is about to conclude the event today, but please check back at gpsworld.com/webinars to find out information about our next event, which is scheduled for July 18th. Thank you again for attending, and thus concludes today's event.